as delta t tends to 0, then these three equations, delta u over delta t, if delta t tends to 0, this may be written as du over dt, which is known as a material derivative or total derivative. Similarly, delta v over delta t tends to 0 may be written as dv over dt, and delta w over delta t as delta t tends to 0 may be written as dw over dt. So, previous three equations can be written in the form of total derivative du over dt, dv over dt, dw over dt. On the right hand side we have these four terms. These four terms are du over del u over del t, time derivative of u, plus u del u over del x, where u is the velocity in x direction, multiplied by gradient of u in x direction, gradient of u in y direction, gradient of u in z direction. So, space derivative del x, del y, del z, and this is time derivative. Now, du over dt is what basically? It is acceleration in x direction, dv over dt is acceleration in y direction, dw over dt is the acceleration in z direction. So, this ax, ay, az may be written in these form, right. If we observe this equation, let us say first equation, in vector form we can convert these three equations into one equation. Now, if we are observing these terms on the right hand side of this equation, then ax is basically del u over del t plus these three terms. So, in these four terms we can divide these four terms into two categories. This is the one term which is time derivative of u, and this is u del u over del x, v del u over del y, w del u over del z, where u, v, w are the velocity in x, y, z direction, and del u over del x, del u over del y, del u over del z are the gradients in x, y, z direction. So, it means that right hand side is divided into two categories. This first part is known as local acceleration. So, del u over del t is known as local acceleration or temporal acceleration, del u over del t, right, and u del u over del x plus v del u over del y plus w del u over del z is known as a convective acceleration. It is due to convection. So, it is called convective acceleration. So, total acceleration is having two parts, one is called local acceleration or temporal acceleration, and another one is called convective acceleration. So, to understand temporal and convective acceleration further, suppose we have a fluid flow where we have a steady and uniform flow, steady and non-uniform flow, unsteady and uniform flow, and unsteady and non-uniform flow. Then what happens to temporal means del u over del t, and convective means u del u over del x plus v del u over del y plus w del u over del z. So, what happens to convective acceleration? So, this material acceleration is summation of temporal plus convective. So, if we have a steady and uniform flow, in this case what happens to del u over del t? Since flow is a steady flow, if flow is a steady flow, then u is not function of time. When u is not function of time, it means this is 0. U does not vary with time. So, this is 0 if flow is a steady flow. We have already studied what is the meaning of a steady flow and uniform flow. If flow is a uniform flow means velocity does not vary in x direction, velocity does not vary in y direction, and velocity does not vary in z direction for three-dimensional Cartesian coordinate system. If velocity does not vary, or velocity gradient in x direction, y direction, z direction are 0 or do not change in x, y, z direction, then this term is 0, del u over del y is 0, and del u over del z is 0. So, it means that right hand side local acceleration as well as convective acceleration both will be 0. So, it means that temporal will be 0 and convective acceleration will also be 0. If flow is a steady and non-uniform flow, If flow is steady, then first term del U over del T will be 0. But if it is a non-uniform flow, it means that velocity vary in x, y, z direction. If velocity vary in x, y, z direction, it means that del U over del y, del U over del x, del U over del z may exist. If these three may exist, then because of this component, which is called convective acceleration, this component may exist. So if flow is steady, this term will be 0, but if flow is a non-uniform, so flow may be steady, but it may not be uniform. So if flow is a non-uniform, then convective acceleration will exist and temporal will be 0, but convective acceleration will exist. If we have a unsteady flow and uniform flow, in that case, if we have an unsteady flow, it means that U is function of time, so it will have time derivative. So del U over del T is not equal to 0, but if it is uniform flow, it means that the velocity gradient in x, y, z directions are 0. It means this term will be 0. Del U over del x will be 0, del U over del y 0, and del U over del z will be 0. So multiplication of U and multiply 0, so it will be 0, V multiplied by 0, 0, W multiplied by 0, 0, and this will exist. So if we have this situation, flow is unsteady and uniform, then local or temporal acceleration will exist and convective acceleration will be 0. Now if we have a fourth situation where we have a unsteady and non-uniform flow, if we have a unsteady and non-uniform flow, in that case del U over del T will exist because it is a unsteady flow, and flow is non-uniform, it means that del U over del x, del U over del y, and del U over del z also will exist. So both local and convective will exist, temporal exist, and convective acceleration. So in case of unsteady and non-uniform flow, both local acceleration and convective acceleration will exist.